Hello everyone and welcome back to Total Organic Chemistry. This video will be the first video that's not any review that I've made, and we'll just be jumping right into discussing functional groups and kind of an introduction to what that means, and then a short lecture on alkanes and their properties and some of their nomenclature. So all of organic chemistry is based around functional groups. And throughout this course, we will be taking functional groups basically one at a time and discussing their reactions, how you make them, what their physical properties are, things like that. And they are very, very important to understand. A functional group is basically a piece of the structure of an organic molecule that determines its reactivity. And functional groups are basically, the idea is that if you have a bunch of molecules and they're all very similar, they might be different, but they all have the same functional group. That means that they will react in very similar ways. That determines their reactivities. So, as an example, we're going to start out this course with alkanes. As an example, CH3, CH2, CH3, and these are all single bonds in between all of the carbons. And this is propane, gas for your grill or for something like that. We'll also later talk about alkenes, which contain at least one carbon-carbon double bond. So CH2, CH2, that's ethylene or ethene. And that's a precursor for a lot of plastics. So if you ever heard of polyethylene, now you know where that comes from. Continuing with this kind of trend, alkynes. These are things that contain a carbon-carbon double bond. And this is acetylene. I've brought up this molecule in previous videos. And this is a fuel for certain blowtorches or welding. We also have things called haloalkanes or alkyl halides. CH3Cl, so chloromethane. And this is used in some situations as an anesthetic. Alcohols, maybe more familiar. So ethyl alcohol or ethanol is just regular drinking alcohol or grain alcohol. And carboxylic acids. We have CH3, COOH. This is acetic acid, which is found in vinegar. Usually vinegar is maybe 4 or 5% acetic acid and the rest water. And there are many, many more functional groups. But these are just some of the most simple ones, and they're ones that we're going to encounter lots. And like I said, we'll discuss more as this course goes on, but these are maybe some just to kind of whet your appetite. So like I said, briefly mentioned that alkanes contain only carbon-carbon single bonds. And that's what determines their reactivity. So, like methane, CH4, doesn't have any carbon-carbon bonds, but it's the simplest alkane. CH4 is methane, which is found in natural gas. It's the main component. We also have ethane, which has 2 carbons. Propane, like I have above, has 3 carbons. And then we can keep adding as many carbons as we want. And it'll just be some number n of carbon atoms in this long chain. And what these are called is a homologous series. This long list of compounds. If you just keep adding one carbon atom at a time, keeping the same structure otherwise, that's what a homologous series is. Adding one carbon atom. And what we can do, let's start a new page here, we can actually draw these as more condensed structures, which is what I'm going to be drawing in the rest of the course. I usually won't write out all of the atoms, CH3, CH2, etc. Instead, if we want to represent this molecule, propane, we can draw this. And these are just called line angle structures, or any other variant of that, where each vertex is a carbon atom and each line is a bond. And all the hydrogen atoms are implied. So we're not going to draw out all the hydrogens. That would be really cumbersome. It would fill up the page real quick. So what we do is we just draw the carbon bonds, the carbon-carbon bonds, excuse me, and each vertex or each end of that line is going to represent one carbon atom. So if we draw something like this, we'd have 4 carbon atoms, and this is butane. These are called straight chain alkanes. We draw a big arrow up here. And that's pretty intuitive, right? Because there's no branching or anything like that. It's just a long chain of carbon atoms. They're all connected to one on the left and one on the right, except for, of course, the ones on the ends. And these are the simplest sort of alkanes. Those are called straight chain alkanes. We also have maybe branched alkanes, where we have some branch here. Or we can even have multiple branches. And these are all kind of subsets of alkanes. We don't define them as their own functional group, but they certainly affect the reactivity in ways that we'll discuss later. We can also have cycloalkanes. That was a terrible cycloalkane. Much better. And cyclo, remember, it's a circle, so it forms a cyclic compound. And those have their own reactivities as well. And for example, just to clarify this a little bit more, if we look at these 3 compounds here, these are all what we call constitutional isomers of each other. You may have heard of this before. where each of these has the same molecular formula, C5, H12, if you can count the carbons. Each of these has 5 carbons, 1, 2, 3, 4, 5, 2, 3, 4, 5, and then the straight chain 1, 5. They all have the same number of carbons and number of hydrogens, but they're just arranged in different ways. We call those constitutional isomers, and we get those a lot with branched alkanes. We can also discuss a little bit about nomenclature. I'm not going to get super into nomenclature, which is the science of naming different compounds, because I don't find it incredibly important when we're discussing organic chemistry through this sort of functional group approach that I'm going to be taking. It's very useful, of course, to be able to recognize a compound and name it, or at least name the most important parts of it, but I won't be asking you or requiring you to name a very, very complex molecule in terms of the systematic nomenclature that's used by organic chemists. It is important to recognize that it exists, which is why I'm going to just give a brief intro. So this system of systematic nomenclature is naming compounds so that they are unambiguous. You can look at one name, you can look at a name of a compound, and you can draw it 100% accurately if you know all the rules. So there's no ambiguity, there's no confusion on how these molecules are named. And this comes from this association, the International Union of Pure and Applied Chemistry, IUPAC, and they have a huge book that has a set of rules for naming all these compounds. The most important thing to know is the list of prefixes, or roots, that come from all the different numbers of carbon atoms in your certain molecule. So if we have a carbon-based molecule with 1 carbon, the prefix is going to be meth, so like methane or methanol. Those each have 1 carbon. We have ethane, so we can draw these molecules below, CH4, CH3, CH3, that's 2 carbon atoms. Prop. Now I'll start drawing these line angle structures. Bute for 4 carbons. And then above that, we start using Greek prefixes, or Greek roots. Pent for 5, hex, hept for 7, and oct. 1, 2, 3, 4, 5, 6, 7, 8, and etc. These are the most important ones. Usually we just work with smaller molecules where the chains are no longer than maybe 6 or 7 long. So these might be good to memorize or to at least get comfortable with, because they will be very useful in differentiating between different organic molecules and their sizes and their structures. The way systematic nomenclature is approached, for alkanes at least, so if we just take a look at just an alkane, remember carbon-carbon single bonds only, and all their associated hydrogens. So this would be pentane. We take our prefix for 5 carbons, and then we add ane for alkane. So that's pretty straightforward. What if we add some branch onto it, like this? So now we have an extra carbon atom, but this is not hexane. Even though it has 6 carbons, it's not a straight chain, so we can't just call it hexane. What we do is we take the longest chain, we find the longest chain in this molecule, which is our 5-membered alkane, the pentane root. So this is going to end in pentane somehow. And then how do we talk about this one carbon right here? We're going to say that's, here, let's draw this with a different color. Say this is blue to correspond to pentane, the longest chain. And then this is going to be methylpentane because of the one carbon attachment. And that's, remember, the prefix is meth, and we add this YL, methyl, to say that it's a substituent, so it's on our main chain. And then, to show us where that substituent is, we're going to number the carbons. So these are 1, 2, 3, 4, 5 carbons, and this is going to be carbon 2. So 2-methylpentane. So why isn't it 4-methylpentane? Is it wrong to number the carbons this way? Well, what we want to do is keep the lowest number possible. So we would rather have 2-methylpentane than 4-methylpentane. Maybe if we name a compound that has more substituents. So what about this one? Well, we find our longest chain again. So that's 1, 2, 3, 4, 5, 6 long. 6 carbons long. So what's our prefix for 6? Sorry, our root for 6. That's hexane. And then our 2 substituents, we have 2 things coming off of it. It's going to be this one here, that's 2 carbons. And then this one here is also 2 carbons. So our root for 2 carbons is eth. So ethyl hexane. But now there's 2 substituents, so how did we signify that? Well, now we use another modifier for multiple substituents. So we say diethylhexane. And then we use our same rules for numbering. So 1, 2, 3, 4, 5, 6. And these are on carbons 3 and 4. So we say 3, 4 dash diethylhexane. And if we numbered the carbons the opposite way, if we have 1, 2, 3, 4, 5, 6, we'd end up with the same numbers, 3 and 4. So in this case, it doesn't matter which end we start at when we number. I'm just going to do one more example. Like I said, I'm not incredibly worried about nomenclature, but it is useful to know where these names come from. Okay, so remember our first step, longest chain, 1, 2, 3, 4, 5, 6, 7 carbons. Sometimes the longest chain won't be as obvious as I've drawn it to be here, but it's important to look at all the possibilities. So 7 carbons, heptane. Now we look at what is coming off of that chain. So we have 1 methyl substituent here, that's 1 carbon, another methyl here, and then an ethyl substituent here, which is 2 carbons, remember. So now we have a problem. We have 2 substituents that are methyl and 1 that is ethyl. So which one do we put first, or does it even matter? It does matter in the terms of systematic nomenclature, and we're just going to label them in alphabetical order. So ethyl, E, comes before methyl, so that means this is going to be methyl second. and then ethyl will be first up here. And then we're going to use the same rule that we did in the previous one. We have two methyl substituents, so we're going to say dimethyl. Let's rewrite all this so I have more room. Heptane over here is our root. Methyl second, because it comes second in alphabetical order. And then ethyl first. We have two methyl substituents again, so let's say dimethyl. And then we only have one ethyl, so we don't have to do anything there. And then the numbering, how do we determine numbering again? Remember, we want the lowest numbers possible. So let's start at this end of the carbon, this end of the chain, excuse me. So then we get carbons 2 and 4 have the methyl substituents. 2, 4, oops, that looks like a 9, 4, dimethyl, and then our ethyl is on carbon 5. So 5 ethyl, 2, 4, dimethyl heptane. And as you can probably notice, these names get really cumbersome really quick. And these molecules only have, what, 7, 8, 9, 10, 11 carbons. That's not even that big of an organic molecule, but these names get incredibly cumbersome. So because of that, for a lot of very common molecules, we simply use what are called trivial names, or historical names. So very common molecules such as this molecule has 4 carbons. Usually we would call that 2-methylpropane. This is a lot of times called isobutane. It's got 4 carbons, and iso is an isomer. Or maybe this molecule here with 5 carbons, neopentane. And all these names are kept for historical reasons, and we will come across many, many of these trivial names with more functional groups. Okay, so that's going to be all I'll talk about for nomenclature. Let's move on to something a little bit more interesting. The physical properties of alkanes are pretty intuitive to understand. So the melting points, boiling points, and densities of alkanes generally all increase as the size of the alkane increases, with more carbons. So these are more, if you remember from general chemistry, more London dispersion forces or van der Waals forces. London dispersion. So these intermolecular forces are what determine melting points and boiling points, remember? And if you have more or stronger intermolecular forces, you'll have a higher melting point or boiling point. And dispersion forces generally increase with increasing size or increasing molecular weight. So more carbons in our alkanes will give higher melting or boiling points. So that means that things like methane or ethane are gases at room temperature. Propane and butane are also gases, but you might have seen them in compressed liquid form. Like if you get a propane tank for a grill or a butane lighter. inside those containers, the propane and butane will actually be liquid. But if you compress them a lot, then they can turn into liquid fairly easily. And then if you keep adding more carbons, you can get into liquids. And if you have lots and lots of carbons, maybe 20 carbons or more, you can start getting into the solid alkanes regions at room temperature. And how can we make use of this in the real world? So in oil refineries, a lot of times what they do is use a system called fractional distillation, where we have this huge column and we put our crude oil in, and crude oil is just a mixture of all of these different hydrocarbons, all these different alkanes, and other molecules that just contain carbon and hydrogen. So we put crude oil in, and then we have a whole bunch of different outlets where we collect different fractions or different portions of that crude oil. And so we might, in a fractional distillation setup, we heat up the column, start boiling away all of these different portions to where we get the light alkanes off the top, like methane. Very low boiling point, so it's very easy to boil off. And those come away all the way at the top. And then we increase in weight to very heavy alkanes at the bottom, like motor oil, things like that. Alkanes or hydrocarbons. Let me clarify that. Hydrocarbons. So these fractional distillation setups are very useful in not just oil refining, but many other situations. You can use it in a laboratory to separate compounds that differ in boiling point, and it's a very easy and intuitive demonstration of how the melting points and boiling points of alkanes or other hydrocarbons differ in terms of molecular weight or size. The last thing I want to talk about for this video is rotation around single bonds in alkanes. So rotation around the carbon-carbon single bonds, or any single bond, is generally very easy. We say that we have free rotation at room temperature because it requires very little energy to rotate around those bonds. And we can use that, we can kind of figure out what that means for us in terms of alkanes to start with, and we will discuss it more again in the future, just like many of these topics. So if we draw a molecule of ethane, remember ethane is 2 carbons, and let's draw it with our stereo projection showing us the position of the atoms in space. Remember that the wedges show bonds coming out of the paper, and dashed ones are going into the paper. So there's a molecule of ethane, C2H6. And what happens if we look at it from this position here? Imagine this is our eyeball, and we're looking down the bond from this carbon here to this carbon. We can draw what we call a Newman projection. And Newman projections are very useful for looking at the angles between certain atoms and for looking at this rotation around bonds. So what we do is the front bonds we draw with these lines like this, and then for the rear bonds we draw a circle and then more bonds coming out like so. So for the front carbon, we have one hydrogen that's going directly up. Let's draw that here. One carbon sort of going to the right, because remember we're looking at it from this eye's perspective. This is the other hydrogen. And then one hydrogen over here going to the left. Similarly, for the rear carbon, we have two hydrogens, one on the right and left, and then one going directly down. And we call this configuration staggered. Because the angle between these hydrogens from the front and the rear is 60 degrees. And this is also very low in energy, because we don't want the hydrogens to bump into each other or to be overlapping at all. So this is very stable, it's in low energy. If we draw another configuration of the same molecule, but instead have the wedges and dashes pointing in the same direction or overlapping, then we can draw another Newman projection, again looking, draw another eye again, looking this way, where we have one hydrogen here pointing straight up, that's our front carbon, and then one bottom left and bottom right. Oops, I'm on autopilot. Okay, so we have these carbons, this carbon in front with the hydrogen on top, and hydrogen to the left and right. And then our rear carbon, draw this circle, remember? But now these hydrogens are almost overlapping, or they are overlapping. So we're going to draw those bonds coming, not quite overlapping, because we're still trying to draw on a flat sheet of paper, but not staggered like it was in the previous one. We have one hydrogen up here that's on top, and then one on the left and one on the right. And this is what we call the eclipsed conformation, because the hydrogens are eclipsing each other, they're overlapping. And this is where the angle between them is 0 degrees. And this is relatively high in energy, because those hydrogens don't want to be overlapping. They don't want to be bumping into each other with their electron clouds. So if we draw a little diagram or a little graph of, we have energy here on the y-axis, and then the angle, this is called the dihedral angle, between these hydrogens, like so. If we imagine rotating it around, we'll get a sort of oscillating sinusoid here. So just an oscillating graph where these positions at the high points are the eclipsed conformations because those are high in energy. That would be when the angle is about 0 degrees or 120 degrees if we rotated another hydrogen around. And these low points will be the staggered conformations. And those are low in energy, and that's when the angles will be around 60 degrees or 180, or any multiple of that. So what if we add a substituent onto our ethane molecule? What if we draw something like butane? And butane has 4 carbons. And draw our structure again. Except now we're still going to be looking down this bond between carbons 2 and 3. Here's our eyeball. So between the middle 2 carbons, we can draw another Newman projection, where this time our top substituent is going to be a methyl group, so CH3. And then our left and right hydrogens here. And then now our rear carbon, we have a bottom substituent that's CH3, methyl. And then our left and right hydrogens again, these two. So because these methyl groups are the largest and they're going to matter the most, they are really going to want to be away from each other. So we can say this is the anti configuration because those methyl groups are opposite each other, or anti. And this is going to be the lowest energy conformer because those methyl groups, like I said, they're going to want to be very far away from each other. So this will be the most stable configuration. If we rotate those a little bit, let's just keep the left side the same. And then we'll rotate this a little bit. So now we have a wedge with the methyl group there and then the hydrogen down here. Let's draw our Newman projection again. And the front one will be the same. If we look at the rear one, we've just rotated it 120 degrees. To where now the methyl group is on the right here. We have another hydrogen and hydrogen on the bottom here. This is going to be our gauche conformer. And gauche means that we're still in the staggered position. We see that these angles are comfortably away from each other. They're not eclipsed. However, the largest groups here are closer than they would like to be. So because those methyl groups are next to each other, we can say this is gauche, and this is low energy, but not quite as low energy as the anti-configuration up here. So now we have one more. Again, let's keep the left side the same. Now this, we will again draw our Newman projection. So our methyl group on top, hydrogens on each side, and now we see that these are eclipsed. We have the methyl group pointing up, just like in the previous molecule when the hydrogens were eclipsed. So that's our methyl group. We're going to put that right about there. And then our hydrogen is on the left, and another hydrogen on the right. So now these are overlapping, and this is again our eclipsed conformation. And this is high energy, especially now that the methyl groups are overlapping. For example, if the hydrogen were overlapping with a methyl group, that would be very high energy, not quite as high energy as this one. If we draw our same sort of graph that we did for ethane, where we have E here, and the dihedral angle here. Now we get sort of an oscillating pattern again, but where the peaks and troughs are now slightly in different positions. So up here, this global maximum, the highest energy, is going to be where the eclipsed methyl groups are. Remember, those methyl groups are pretty big. They really don't want to be next to each other. These local maxima are going to be where the eclipsed hydrogens are. Or if the eclipsed methyl group over a hydrogen atom were in our conformation. Then we have a local minimum here. That's going to be our gauche conformation, where the methyl groups, again here, are staggered, but they're next to each other. And then our global maximum here is anti, where the methyl groups are completely opposite. And that's going to be very favorable. So that wraps up my introduction to alkanes and some of their properties. Thank you again for watching Total Organic Chemistry. Please be sure to subscribe and check out my Patreon page for extra supplemental material that I will be uploading. And I will link that in the description.